In this lecture, we will look at the exact definition of covariance between two random variables, and it's useful if you have some intuition about covariance before watching this lecture. This is the starting point. I have two random variables, x and y, and I'm denoting the expected value of x by mu x and the expected value of y by mu y, where mu x and mu y are simple constants. If I subtract the expected value from x, I get x minus mu x. This will be a new random variable with expected value 0. So it's simply a centered version of x. If x is continuous and the PDF of x looks, I don't know, something like this, then the PDF of x minus mu x will have the same PDF, but it will be centered at 0, something like this. I can create a centered version of y as well. So when y takes a value larger than its expected value, then y minus mu y will be positive and vice versa. The covariance between x and y is based on creating a new random variable z, which is the product of these two centered versions. So it's x minus mu x multiplied by y minus mu y. If we only consider the sign of z for a while, we see that z will take a positive value when both parentheses are positive or when both of them are negative. So z will take a positive value if x is above its expected value and y takes a value above its expected value. Z will also take a positive value if x goes below its expected value and y goes below, while z will take a negative value if these two terms have different signs. If x goes above its expected value and y goes below its expected value, then z will take a negative value. Finally, we simply define the covariance between x and y as the expected value of this new random variable z. So if z mostly takes positive values, then the covariance will be positive and vice versa. So we can see that the covariance of x and y will become positive if it's more common for the product of these two terms to have the same sign. The covariance of x and y is positive if, whenever x is greater than its expected value, y tends to be greater than its expected value. The covariance will be negative if it's more common for y to be below its expected value when x is above its expected value. Then the product of these two terms will be negative. Here is what we have. We define z as this product. It's a function of two random variables, x and y, and we simply define the covariance of x and y as the expected value of z. Putting it all together, you see the definition of covariance the way it's typically displayed. We also have this alternative formula for the covariance, which will follow from this one simply by multiplying out this parenthesis. So this is the definition of the covariance, but it doesn't really help you if you want to calculate the covariance. To calculate the covariance, we need to use the formula for how we calculate the expected value of a function of two random variables. We have two different formulas depending on whether x and y are continuous or discrete. So let's start with the discrete case when the covariance will be a sum. Remember, for the discrete case, we have the following result. The expected value of a function of g of x of y is equal to the sum over all possible x values. I go from 1 to n. Sum over all possible y values. G xi yj times f xi yj, where f is the joint probability mass function. For the covariance, this g function is then equal to xi minus mu x multiplied by yj minus mu y. So by just plugging this into this formula, we get the covariance of x and y. A little bit more formalized, The range of x is from x1 through xn. The range of y is from y1 through yn. Then the covariance of x and y will be given by this double sum, where n and or m may be infinite. An example of how we would calculate the covariance between two discrete random variables. In this example, n is 2, x1 is 0, x2 is 1, m is 2, y1 is 0, and y2 is 1. We have the following probability mass function. Even before we calculate the covariance, we can see that the covariance will end up being positive, since we have the bigger probabilities here and the smaller ones here. We see that it's much more common for x to be low at the same time that y is low, and x to be high at the same time when y is high. So we can identify a positive covariance between x and y. Exactly what it is, we need to calculate. Before we continue, we have to find the expected value of x and y, and they come out to be 0.5. So to find the covariance, we simply have to go through all 4 possible values. Starting here, we do xi, which is 0, minus its expected value. So that comes out to be minus 0.5. We do yj, 0, minus its expected value, 0.5. So this comes out to be minus 0.5 as well, multiplied by the PMF of this one, which is 0.4. So this first term was the case I equal to 1, j equal to 1. Then we move on to the second term, which is I equal to 1, j equal to 2. That is this one right here. xi is the same, so we get the same value. Now yj is 1, and 1 minus a half is 0.5. The PMF in this case is 0.1. Do the same thing. This one is when I is 2 and j is 1, and this one is when I is 2 and j is 2. So now we have all 4 terms. All we have to do is just sum this together and we get 0.15. We have an alternative formula for the covariance. This one right here, we can calculate it as the expected value of the product and then subtract the product of the expected values. To find the expected value of the product, you do the same thing as we did with the covariance, but you don't subtract the means. If you do that, you will get that the expected value of the product is 0.4. So the covariance will be 0.4 minus 0.5 times 0.5, which will give us the same answer, 0.15. So let's move on to the case when we have 2 continuous random variables. For the case of 2 continuous random variables, the formula for the expected value of a function of 2 random variables is the integral over the x variable, the integral over the y variable, g of xy, f of xy, dy, dx. Where in this case, this is the joint probability density function. For the covariance, this g function is simply x minus mu x, y minus mu y. And if I replace this with my g function, I have the formula for the covariance in the continuous case. Summarized neatly here, the covariance between x and y is given by this double integral. An example of how covariance is calculated. In this case, I have a joint PDF, which is x plus y, the range of x, range of y. You can find the expected value of x and the expected value of y to be 7 over 12. For example, to calculate mu x, you have to calculate x from 0 to 1, y from 0 to 1, x times f of x, y, dy, dx. If you calculate this double integral, it comes out to be 7 over 12. So to do the covariance, the integral of y, integral of x, this is my x minus mu x, this is my y minus mu y, this is my f of x comma y. All I have to do is just calculate this double integral. If you do that with Maple or by hand, you should come up with minus 1 over 144. And you always have the alternative to calculate the covariance as the expected value of the product minus mu x times mu y. If you do the expected value of the product, you don't subtract 7/12 from x and y. So expected value of xy will be x times y times f of xy, comes out to be 1/3. If you then do 1/3 minus mu x times mu y, you come up with exactly the same answer, minus 1/144.